All right, there we go. Awesome. Yeah. So okay. So yeah, the 137 is the same on both sides already. So the decay particle should have a mass of 0, and then we have 55 on the left for the atomic number, and then 56 on the right. So we would need something with a -1 charge, right? Because it'll be 56 minus 1 to give you the 55 on the right.
Uh, is that right? It's adding a positive charge, right? Because you have 55 and then you're going to 56.
Yeah, so here, let me write it again so we can see it better.
Okay, from cesium to barium, I thought.
Yeah. So the masses, we want the same on both sides and the atomic number as well. So,
Okay. So
so
you're adding it to the right so that if you were to switch it over to the other side, it would be a positive beta particle. Is that what you're saying?
oh yeah, that could happen. So, but yeah, here on the left we have an atomic number or charge of 55, and on the right for barium it's 56, but we want it to be 55 on the right. So it
Okay.
would have to be a -1. So that's why, so it would be like 137 plus 0 is 137 on the left, and then 56 plus -1 is 55, which would match up with the cesium on the left.
Got it. Okay. I guess that makes sense as
Yeah.
why it would be a decay. So it's just really I guess how you're writing your formula. Like if you're writing the formula from so that's cesium 55
Yeah.
goes to barium 56 plus a negative beta particle.
Yeah. So for all of these types of decays, you're getting one thing on the left and more than one thing on the right. So you could so like this one, so this one here is beta decay. And when they say beta decay, they mean beta minus decay. Because positron is also beta, but they would call it explicitly positron. So if they just say beta, that means it means the negative one. But here we can see that this is positron emission. And you have a proton on the left and then the positron and neutron on the right. And then here you have this is actually also beta decay, where you have neutron on the left and then two of the things on the right. So that's how they'll be written. They'll be written with one thing on the left and then what it decays into on the right, as well as the decay particle.
Okay.
Unless it's electron capture, which is what I mentioned here, because this is really just going to be, you know, proton plus or proton 1 plus 1 plus electron, which could be, -1 and then 0, giving you the neutron, oops, with the mass of 1 and charge of 0. So for electron capture, that's the only thing that's not, I guess, technically decay. And since it's not technically decay, you have two things on the left rather than two things on the right.
Okay. Thank you. That's really helpful. So yeah, I guess so yeah, for an alpha decay, you would notice a mass increase of 4 and a charge increase of 2. It just like you'd always notice it in that order, I guess. So if you have like say a cesium atom and it was 141 and then it had a charge of 157 or 57 or something, you know that it was a alpha decay or okay.
Yeah. If you, yeah. I think the biggest giveaway for alpha decay is a change in mass
Okay.
because
Yeah.
it's the only decay.
It changes the mass.
Yep.
Okay. Got it. All
Mhm.
right. That's really helpful.
Uh, yep. And yeah, if you wanted to take a screenshot.
Oh yeah, I'll take a screenshot real quick.
Yep.
All right.
Mhm.
Right. I went through a lot of these a little bit already,
Mhm.
but let's see. Which ionic radius? Okay, yeah, I think
Yeah. So um, yeah, almost everyone gets this wrong. So basically, um, you're probably thinking of the periodic trend for atomic radius, right?
yeah. In this case, it's because this has more like electrons that are um, just unbound, and so it's more likely to lose them, maybe, or
Oh, so okay, so you're already aware of the periodic trend of atomic radius.
a little bit, yeah. But I think,
Like basically, if we go in this direction, we have an increase in electronegativity, electron affinity, ionization energy.
mhm.
But
But downwards it would go increasing radius.
yeah, so if it was like that way, left and down, it's increase in atomic radius.
Mhm.
Okay, so that's one thing. Now, ionic radius is the size when it's an ion, right? So,
Okay.
let's say that we had, let's just say to make this let's say simple, I'm going to make a nucleus with two positive charges and I'll make an electron. Actually, I'll make the nucleus just one positive proton and then just one electron around it. Um, this would, oops, all right, I'm actually, okay, one proton in the nucleus and then two electrons. Uh,
Okay.
so basically the proton will be pulling electrons towards itself because of the like opposite charges attracting. And
Mhm.
that gives this atom a certain size, an atomic radius. Um, now let's see what can happen if we change the number of um,
Electrons.
yeah. So actually I'm gonna go back to putting the two protons here. So okay, two protons in the
As you increase the number of negative charges, the pull and the attractive force to the nucleus, which is positive, uh, decreases because there's more. And then as it continues to grow, as the negative charge grows, the
yeah, yeah,
less you have the less pull you have towards its nucleus, right?
yep, exactly. Yeah, you explained that perfectly. That's right.
Okay, yeah.
Yeah.
I think I definitely misunderstood the the question then. Yeah, now that I look at it, I'm like, oh, I was thinking maybe atomic radius or something
Yeah.
because it looks like it kind of goes down from what was the other one? Nitrogen. So yeah, nitrogen's way over here. I was like, oh, okay.
Yeah. And then so yeah, you definitely had the right idea in terms of atomic radius. But yeah, it's ionic radius. And yeah, so any given atom, the anion will be larger than the cation, right?
Right. Yeah.
Yeah.
Yes. Yeah. That makes sense.
Mhm.
Okay. Awesome.
Yep.
Yeah. That diagram is actually really useful because it definitely illustrates like as you like increase your negative charge, the less pull the nucleus has on those charges.
Yep.
Okay. Let's see. Got this one wrong. Yeah. Group 1A react with nitrogen, form hydrides. Yeah, I don't think I wasn't conceptualizing this right, I don't think.
Oh yeah, this is just kind of like just like something that you have to know.
Yeah.
Um,
Uh, so group 1A reacts with water to form hydroxides, and we're talking about this row, right? Group 1A, and it's just like the alkali metals just react with water to form hydrates. I don't know. So is this just like a memory question, I guess? Like you just have to know that.
yeah. Like yeah. So basically the idea is that these group 1A alkali metals um are actually bases. Like they can like when you put them in water, they turn into a base, like an Arrhenius base, which is when a base causes a hydroxide to form.
Mhm.
So that's also why, like, have you ever seen or something where like they put like raw like pure sodium in water? It like explodes basically.
Okay, interesting. No, I have not seen that, but
Mhm.
um, that's interesting. Okay. All right. Yeah, I'll probably just need a review. Are there other questions like that? Will just be like, um, I don't know,
Uh,
like you reacted with some other thing, and it's it makes
yeah, I think group 2 might have issues with solubility.
okay.
So I think B would be probably true if it would mention group 2A,
Okay.
because a lot of
Okay.
like yeah, but that also depends. But yeah.
All right. I'll probably just need to review
Mhm.
whatever that is. What category of chemistry would you say that is? It's just periodic trends. Is that like
Yeah, it's like a very, very tiny detail for the trends, but
okay?
I think you would just know it from this, and you're likely not going to see anything else like that. Yeah.
Okay. Cool. I'm just gonna move on. Um, Second ionization energy. I kind of did a deep dive on this on Wednesday when I was kind of going over stuff because I was trying to figure out. I was trying to remember what that actually meant, the ionization energy,
Yep.
and it seems to be the amount of energy required to pull an electron away from
Hmm.
um, away from a neutral atom,
Yep.
right? So you have certain shielding electrons, lithium. For I think it has like three, right? Um, yeah, it's three electrons, which means it has one electron in its valence and two shielding electrons. So it has a repulsion force from those two shielding electrons that push it away, and So it has a greater second ionization energy because pulling two shielded electrons is obviously harder.
Yeah, I think so the way that I see it is like, okay, let's say we have the lithium. So what would happen after it gets ionized, like first ionized?
It would turn into basically like a helium,
Mhm.
like a helium molecule, right?
Yeah, and it wants to be here.
Right.
Doesn't want like everything wants an octet, so it wants to be here. So its second ionization energy, something that would make it go from here to something like there, would be really high because it wants to be that helium.
Mm.
So and then like let's say for beryllium, first ionization would give it the same electron configuration as lithium, and then um second would give it the same configuration as helium. So beryllium is going to have um, a low second ionization energy, but a really high third ionization energy. I mean, I haven't seen any question that mentioned like the third
Like
ion
a third. Yeah.
would have that because idea is just that uh, is once it gets to that electron once it
Octet.
filled, yeah, it's really satisfied like that, and it would take a lot of energy to remove an electron from that octet. Yeah.
Okay. Yeah, that makes a lot of sense.
Mhm.
Yeah, I don't think I when I was answering the question, I just didn't remember what that meant, and
Mm.
didn't make a lot of sense. But I
Yep.
think I think I understand it now. But yeah,
Mhm.
that was just not understanding, I think.
Mhm.
Um, and let's see, we get that one. Okay, yeah, we get into solubility,
Yeah.
and I forgot a lot about like setting up a problem like this,
Yeah.
and whole this whole thing right here.
So anything with that big K is something that it's called a law of mass action. So this includes like KSP, KEQ, KA, KB, KW, K, every K thing that is.
Okay.
Um, and what this means is like, let's say I had a reaction like this. The K would be, so it would be products, and the coefficient, which would be like the number in front of the
Mm-hmm.
product, is going to
To
be the
this.
exponent.
Okay.
So this would be um
A to the little a times b to the little b kind of thing.
mhm.
Okay.
Yeah. So that's so essentially what the setup for any K thing, capital K thing will be.
Mm-hmm.
Um and we and since these are concentration values, we don't include pure substances because we like that would be like 100%, whatever that thing is. So okay, let's see. So they're talking about barium sulfate, barium SO4, and it would dissociate into barium 2 plus and then SO4 2 minus, right?
Mm-hmm.
Um, this would be a solid, so a pure substance that we don't include, but these would be aqueous, so we would include those. So our K or KSP we can set equal to the barium concentration times the sulfate um, concentration. And we won't have anything in for the reactants because the reactant is a pure substance, so we don't have any denominator here. And and then we can set this equal to the value that they gave us. They said 1.1 times 10 to the negative 10. Now, solubility that we can solve for now would be if we assigned, let's say, like a variable x for these.
Mhm.
Like, let's say this is x. I mean, so the amount of this barium ion and the sulfate ion should be
Yeah,
equal, right?
right. Yeah,
So,
there's 1 mole barium, 1 mole sulfide.
yep.
Yeah.
So we can set each of these equal to x to get you x squared is equal to 1.1 times 10 to the negative 10.
Mhm.
And now what do we do to solve for x?
Yeah, take square root, basically assign it to the 1/2 power. You
Uh-huh.
can just take a half of 10 and get 1.1 times 10 to the negative 5. So yeah, that makes sense.
Yeah. Now there's two variations that you'll see. Um, I'll write them here on the left. So like, let's say we had something like this, like that. Uh,
uh
uh, this would be like, we can call this x, but this would have to be
X
2x,
squared, or 2x. Okay.
yeah, in parentheses squared.
Yeah. Oh, okay.
And
So
then,
it'd have to be 2x squared.
mhm,
Okay, I got it.
yep. So then, this would be, if we multiplied this would be x times the 2x squared, the 2 inside the parentheses, you square to get 4, and then you square the x as well to get x squared. And then this would be 4x cubed, right?
Yeah.
So that's
Have that.
yeah, that's one other variation. And then the third type of variation would be, I mean, I can't think of like an actual, like I'll just use kind of like this, but let's say it's something like this plus 3x like that. Um Here we can say that this would be x, and then this would be 3x in parentheses cubed, so that when we multiply this, it would be x times 3 cubed would be 27 times x cubed, and then this would give you 27 x to the 4th power.
Okay.
So basically, these are the three variations you'll see. You'll see an x squared, you'll see a 4x cubed, and you'll see a 27x to the 4th power.
Okay. So like those are basically the main MCAT variations that they give you.
Yeah.
Okay.
Mhm.
That's cool.
Mhm.
Yeah, that was I think that's one thing that I forget how to set up
Mhm.
sometimes is just the KSP and what that looks like.
Yep.
I know I've like in my course of studying I have seen this. I just don't think I've practiced it enough. So I need to kind of do some more practice questions so I can recognize how to solve it
Yep.
each
Yep.
time.
Yeah. Yeah. This law of mass action is the case for all of the K stuff. Uh, so yeah.
Okay, awesome. So I can I'll take a screenshot of this real quick
Mhm.
so I remember. All right, let's here. Yeah, I forgot what the molecular formula, what bicarbonate was.
Mhm.
I think that's just another thing you have to just know.
Yeah.
Yeah. Um, so yeah, I probably just remembering
Mhm.
certain general chemistry nomenclature there.
Yep.
Let's see. Cations. Oh, yep. I forgot my the definition for the difference between Bronsted-Lowry and Lewis. Um, Lewis is like your acid is the electrophile, I believe.
Yeah, so when so generally when we talk about acids and bases, we are
Mhm.
talking about the Bronsted-Lowry definition. So an acid would be a proton donor, a base would be a proton acceptor. So that's just if they mention acids and bases. But if we're talking about electrophiles and nucleophiles, which is basically what organic chemistry is,
Mhm.
the nucleophile would be the Lewis definition of a base, and the electrophile would be the Lewis definition of an acid. Um,
Right.
and a carbocation is kind of like, if you have um, like a molecule that has like a leaving group that leaves. Um, so basically, I guess the carbocation would be the electrophile. Like let's say it's something like
Yeah.
this.
It's got a positive charge on it.
Oh yeah, I forgot. Yeah, positive charge. So water could, attack it, right?
Yeah.
And water, if water's the one that attacks it by donating its electrons, that makes water the nucleophile and the carbocation as the electrophile.
Okay. And let's see. So the electrons coming from the oxygen. So the oxygen would attack, and forget how that works. Is hydrogen would then leave, right? And then would it create like a hydronium from
Uh,
that, or
let's see.
would it be hydronium? So H, and then another water molecule pulls hydrogen off.
Yeah, something like that.
So something like, yeah. Okay, cool.
Mhm.
Sweet. Okay. Yeah, that was something I was just forgetting what the difference was. And yeah,
Yep.
that helps. And let's see here. Oh, yeah. So difference between galvanic and or just what happens in a galvanic cell. I was forgetting that oxidation happens at the anode. So you have like your what is it? It's like a zinc and copper, right? Um, zinc and copper. I think zinc is the source of positive. I think it's positive, right? And then um, zinc.
So I don't know about those specific ones because I would
Yeah.
need to have I would need to know their half reactions
Mhm.
because whichever thing has a higher reduction potential would be the
Yeah.
would be the thing that gets reduced, and whichever has a lower
Yeah.
reduction potential will get oxidized. But what's always going to be true is, like loss of electrons, like oxidation Leo,
Mhm.
gain of electrons reduction, but also anox and red cat,
Yeah.
oxidation
Okay.
the anode, and then reduction at the cathode. So uh, this
Okay. Yeah,
this
that's actually a really good one. Good mnemonic.
yeah, so this can be confusing in the case of electrolytic cells because in a galvanic cell, the anode is negatively charged and the cathode is positively charged. So it makes sense that this would lose electrons to give, because if it's negative, it has an abundance of electrons, and this cathode is positive. It's deficient in electrons. So it makes sense that electrons will go from the negative to the positive, right?
Mm-hmm.
But
Yeah.
in electric
Electrolytic.
cells,
Just
the
power source, right?
anode is, yeah. So yeah, and the anode would be positive and the cathode would be negative. Now this may seem like it would cause electrons to flow from the cathode to the anode,
Mm-hmm.
but in, I'll just use like a regular battery here. In an electrolytic, you're plugging this into an external source of electricity, which means that these electrons are
That's
coming in, and
yeah, okay.
momentarily we want this anode here to be positive and the cathode here, because you want the electrons to go to the anode. So it's momentarily going to be positive, even though it's negative normally. Like, okay, I should draw like, okay, beginning situation would be positive here, negative here, and
Yeah,
electrons going this way, right?
right.
So this happens until you have equilibrium, which means no more charge separation,
Mm-hmm.
because enough electrons left the negative end to give you a charge of 0, and enough has entered the positive end, giving you a charge of 0. So there's no electricity flow here. So this is when the battery is dead. And what do you do then? You charge it. And you charge it by plugging it in and then forcing the reaction to run backwards. And the electron source is coming from something else entirely. So so here, this electron, the anode is where the electrons are leaving. So that's where it's being oxidized, and the cathode here is being reduced. And redox means that there's a redox pair. It means that the thing that gets oxidized is going to reduce the thing that, well, the thing that gets oxidized, you got to know what I mean, right?
Yeah, yeah, I know what you mean. Yeah,
So
I get it.
that's redox pair exists here. But in an electrolytic cell, the redox pair does not exist because the electrons are not leaving the cathode. And so essentially, even though we have opposite signs here,
Yeah,
what will
to
never,
me, it just looks like you've created a gradient in the other way. So you
yeah,
just yeah you plugged it into a power source which has a reservoir of electrons that is higher has a higher concentration of electrons on one end than the other, and
yep,
you're pushing that flow in the other direction.
yep,
And you unplug it. Now this side has the reservoir and then discharges to the other.
yep,
Right?
yep.
Yeah.
So basically, these two things are always going to be the case. Well, they'll either be the case or they won't, but it won't ever be like you won't ever have the anode be getting reduced, and you won't have a cathode getting oxidized. So
Okay.
that's, yeah. So the anode will always be the one that gets, so like either it's like this where the anode gets oxidized and the cathode gets reduced, or it's
Mhm.
like this where there is no redox happening, but you'll never have reduction at the anode and you'll never have oxidation at the cathode.
Okay.
So so yeah.
Sweet. Yeah, that was yeah, another thing that I just wasn't. I
Mhm.
guess I just didn't click.
Yep.
Yeah, it makes sense. Just got to review that some more. Just make sure that it really it's like the
Mhm.
anode.
Yep.
I think maybe the picture might have helped if I drew it. I don't know.
Mm-hmm.
All right, we'll go in here. So we exhibit the ion standard vector potentials, aqueous solution. Metals the strongest reducing agent. Okay.
Okay. I see what you did.
Yeah.
So the one with a higher reduction potential is the one that will be most likely to get reduced.
Oh, okay. Yeah.
But if it's reducing something else, which means it itself gets oxidized.
Oh, I see. Okay.
Yeah. It's like reducing agent um oxidizes, or rather,
Gets oxidized as opposed, most likely, as opposed to the thing that get most likely to get reduced.
yeah, the reducing agent reduces the oxidizing agent, which oxidizes the reducing agent.
Okay. I see. Okay. And so in this case,
Yep.
we know that this one is going to be the reducing agent
Mhm.
because it has a, what is this? It's the higher, or a,
Yeah.
because it's just more likely to get, I guess it's just more likely to get reduced.
Yeah, the whichever thing has a higher reduction potential is going to be reduced.
Okay.
But if it is a reducing agent, it reduces other things.
Okay.
And if
So
it
it's
is
most likely just give up its electrons.
so if it yeah, so if it reduces other things, it itself gets oxidized.
Okay.
So 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 here the reducing agent reduces the oxidizing agent, but the oxidizing agent oxidizes the reducing agent. So in other words, this one would be the most likely to be reduced, which means it's the most likely oxidizing agent,
Mhm.
whereas this one with the smallest reduction potential is going to be the most likely to be um, oxidized, which means that it's a reducing agent.
Got it.
Yep.
Okay. Got it. So lower reduction potential means reducing agent. Higher reduction potential means oxidizing agent.
Mm-hmm.
Okay, got it.
Yep.
Sweet. And resonance form of NTO is its most stable structure. Okay. Let's see.
Yeah, I think this question has a mistake in it, to be honest.
Yeah, because I was like,
So
like
we don't.
feels like this is balanced, but I don't know.
Yeah, I think we don't have to worry about this one.
Okay, cool. And have you like looked at this and um, gone through why it could be a mistake?
I think when I looked through this, I was seeing that there's uh more than one uh thing that says
Oh,
as whatever, negative
-1.
oh wait, no. And not that.
To me, it looks like the distribution of charges or something just doesn't seem right. What is this? Nitrogen, oxygen. Nitrogen. So yeah, like nitrogen maybe has an extra pair of. I don't know. Yeah. Well, we can skip it.
Yep. Yeah, we could even do like some of the physics stuff that's towards the later end.
Yeah. Let's go through. Let me look at, because I think like sound and maybe some fluids was something that, because I think it's always Poiseuille's equation or something that
Yeah.
I don't know. It's always like the radius to the fourth or the third power or something that I always get confused.
Yep.
Really just remembering it.
Mm-hmm. We can kind of like just keep it next.
Oh, you want to just keep it next? I think if I just
it doesn't open it in a way that lets you like see all of them.
Okay.
You know what I mean?
Yeah.
It like doesn't let you hit navigate and let you see all the questions.
It does. Yeah. It just kind of like gives you which one. So I'm not really sure what category it's in.
Oh yeah. It's probably going to be like somewhere like in the 50s or something.
In the 50s. Okay.
Yeah, just my guess.
Could have been one of my flag ones. Let me just try one of these.
Yeah, here we go. Yep. So yeah, we're in physics territory now. So yeah, this is another one that almost everyone gets wrong.
Okay.
So
Fill liquid mercury. Yeah, you've probably seen this one many times. And
mhm.
I don't exactly remember what I did to solve this. Setup shown as height equal to 50 centimeters. What is the pressure of air inside the balloon? P naught to be 1 times pascals, density of mercury, 14,000 kilograms per meter cubed, gravitational potential, 10 newtons per kilogram. Okay. Yeah, so for this one, even down, probably good.
What are you trying to do?
I'm just trying to remember, like, I just want to see what my math was on this one.
Let's talk about it conceptually first. So
Okay.
what's kind of happening here?
So it looks like you got a column of air pushing, what is it, mercury or?
Mm-hmm. Yeah,
column of air pushing fluid into a tube with a balloon on the end.
okay.
Yeah.
So let's see. If we had something like this where the levels are equal.
Mm-hmm.
Well, we also have this side open to the atmosphere, right?
Mm-hmm.
So this should be the pressure from the atmosphere. This should be the pressure from the balloon.
Okay.
So if the water levels or mercury levels are equal, these should be equal pressures, right?
Okay.
All right, now what if it's like that?
Means the pressure from the balloon exerting greater pressure than the atmosphere is pushing down on the fluid.
Yep. Now for this.
In this case, the atmospheric pressure is greater than the pressure from the balloon.
Good. And what is the atmospheric pressure?
1 times 10 to the 5th pascals, it looks like.
And what about how much would it be in kilopascals?
Kilopascals, 1 times 10, at least 1 times 10 to the second power.
Yep. So like 100, right?
Yeah, 100. Yep.
So, and they're asking us to find what?
Let's see. Pressure inside the balloon.
Mm-hmm. So we know it has to be less than 100 kilopascals, right?
Okay.
So we could
So
get.
then isolates it to C and D.
Mhm.
Okay.
Yeah. And now that formula for like the gauge pressure or whatever, it's like, oops.
Yeah, I don't remember. It's atmosphere plus something.
Yeah. Basically this.
Gravity type. Oh, okay.
And here we can make this like water column here, like with this height. Um and for the balloon, we can just have it be subtracting that height, or yeah, like that value. So it would be like pressure of the balloon would be the atmospheric minus the rho gh.
Okay.
So that would be whatever, 100 kilopascals minus, let's see, 14,000 times 0.5 meters times 10. So
Okay.
7,000.
So it's 70,000.
Well, okay, let's see. I think this should then be in pascals. So 1E5 pascals. If I subtract this, okay, this is 7E4.
Yeah.
Which is 75. So it's like, wait,
So you got
0.3,
0.5.
0.3 E5 kilopascals. Oh, sorry, pascals, which is 0.3 E3 pascals. Sorry, kilopascals. And I move this over to get the 30.
30 kilopascals.
Yep.
Got it. Okay.
Mm-hmm.
Yeah, and everything's got to be in meters. That's why you convert to meters.
Mm-hmm.
Got it. Okay. Yeah, that makes sense. Yeah, I don't think I remember the gauge pressure equation. So yeah, I mean, I could probably isolate it to C and D if I were to just conceptualize that first part there, where you're just like, okay, you have higher atmospheric pressure on that side. Your atmospheric pressure is supposed to be 1 times 10 to the 5th. You look at look at your units. It's all in kilopascals, and then you know that it has to be at least less than 100. So that makes sense.
Yeah.
All right. Sweet. I'm gonna take a screenshot of this real quick.
Oh, and yeah, knowing that a Pascal is could be deconstructed as a Newton per square meter. Also,
Oh, yeah.
because yeah, like the rho here would be kilograms per cubic meter times the 0.5 meters times the 10, which is 10 newtons per kilogram.
Mhm.
So the meter here cancels out, and we get square meters here. Kilograms cancel out, and so we have Newton per square meter.
Got it. And
Pascal.
which is a Pascal.
Yep, and
Okay.
that's why we were able to subtract.
Yeah. So there's a lot of like, I see why it's hard because there's multiple like dimensional analysis that
Mm-hmm.
you have to kind of go through. Um, Many layers of
Yeah.
conceptualizing and remembering stuff.
Yep.
Okay. Go to the next one here. Diverse submerged in the ocean descends from a depth 1 meter to a depth of 2 meters. Approximately what percentage does the absolute pressure experienced by the diver change? I wasn't really sure how to conceptualize this, and at the time it was just like, okay, it went from a meter to a whole other meter, 100%. So, um,
Yeah. So, I mean, the gauge pressure thing could be used here, but there's also a good kind of rule of thumb to kind of remember, which would be that as you descend 10 meters um, of water, uh, it would add 1 ATM of pressure.
okay, and that's because of what is that? Density of water, or how does that play? Okay, yeah, fluid density of water is 1,000 kilograms per meter cube.
Yeah,
Acceleration of gravity. Okay, yeah,
it's like for the gauge pressure where it's like atmospheric pressure plus rho of water times the G and H. And for, if you, so like this would be a way for you to, I guess, calculate it with the height being kind of like the difference in height here. But yeah, this could also, if you had this like memorized, you would see that um yeah, if it's an increase in 1 ATM of pressure, if every 10 meters, if it's a change in 1 meter, it would be an increase of 0.1 ATM, right?
okay. That's a useful
Yep.
thing to remember there.
Mhm.
Let me screenshot that real quick.
Okay, the Titanic is 4,800 meters underwater, and the pressure is around 400 atmosphere.
Okay, so the pressure is 4,800 meters underwater,
Mhm.
and the pressure is 400 atmosphere.
Yeah, you could even do dimensional analysis here, like 400 meters, and the conversion factor would be this for every 10 meters. It's
Yeah,
1 ATM.
480 atmospheres.
Yep.
So
Oh yeah, I said 400. It's like
yeah,
around like, yeah, I guess like 4,800 or something like that. Uh,
round.
I guess
Yeah,
it's not,
not 1 to 1, but it's close.
yeah.
Yeah.
Because also I think that this is for regular water, but not salt water.
Salt water. That would make sense.
But yeah, that's
Okay.
yeah, it's just a yeah, it's a good kind of
It
version back.
gets you in the ballpark for a multiple choice question.
Yeah.
Okay, that makes sense. All right, let's move on. Okay. I remember doing a lot of these problems for
Mhm.
I guess maybe it's a little different for like differential equations, but they'd always have like a problem kind of like this where it's you have a portion coming out here and then you have a little bit and you have some other brine solution coming in at the same rate. I
Yeah.
just haven't done any of that in such a long time.
Yeah.
So
Yeah. Yeah.
yeah.
Yeah. So this thankfully isn't going to be, you know, anything like that.
Mhm.
Um, but for okay, so for this type of so yeah, this is like the static fluids or whatever. Um,
Mhm.
wait, that's weird that they're still well, whatever. I guess they're using Bernoulli, but you can use so any type of scenario where you start off like if I so yeah, let me draw this scenario. So like let's say that you have some ball here and this is a height h and the ball and this person gonna drop this ball. So but at this point up here right before he drops it, it's not moving, so its initial kinetic energy would be 0 and its gravitational potential energy will be, mgh, right?
Mhm.
And then as it falls, its gravitational potential energy gets converted into the kinetic energy. So
Right.
at the bottom, the final kinetic energy is going to be the initial gravitational potential, and the gravitational potential, like at the bottom, at a height of 0, will be 0, right?
Mhm.
So if we did this, conservation of energy, like uh, initial kinetic plus initial gravitational potential is equal to final kinetic plus final gravitational potential, we have 0 plus mgh is equal to, oh, well, it's equal to this amount, but we can still say, mv squared. So
Okay. Yeah.
mv squared plus 0. And so we get basically these two. We can,
Divide out the masses, multiply by 2, gravity times height,
yep.
and
So you
then
would assume
getting it.
that final velocity is square root of 2gh. And this is true for any situation like this where you start off with 100% potential energy and 0 kinetic, and then
Mhm.
it falls and has all of its potential energy, gravitational potential energy converted into the kinetic energy. So this works for this example of a person dropping like this ball. It also works for if there's an inclined plane and they're like, okay, what's the speed? What will the speed be once it reaches this base?
Mhm.
You could also do it for that. And then this question, you could also do it. So, I mean, they use Bernoulli's, but you don't have to because it's not really flowing here. It's kind of like just coming out and free falling like a projectile.
Yeah.
So yeah, so you could use this equation. Oh, and then you just have to rearrange it for height. So that would be like VF squared divided by the 2G to give you the H.
Okay. Yeah. Makes sense. Yeah, it all derives though from the kinetic and potential energy equations
Yep.
being equal, and that's the setup I was missing there, is putting that into account. So you start out with zero kinetic, um, change your variable, put your variables in, that kinetic final, uh, 1/2 mv squared,
Mm-hmm.
something I got to remember, and then you have okay, and then zero. What is it? Zero kinetic energy at the end. At the end of the, is that potential or kinetic energy at the end? So plus zero.
Yeah, so the energy gets completely converted into kinetic energy like right as it hits the ground.
Mhm.
So you definitely have that kinetic energy value as the non-zero value
Mhm.
at the bottom. Yeah.
Okay, gotcha. Cool. Yeah, that makes sense.
Yeah, I've seen like numerous questions like this, like from different sources where like they give you questions and they solve it using some other like method, but I've seen many of them, being able to be solved this way. So
yeah, I would much rather. I mean, the I guess you could use, yeah, Bernoulli's equation, but this way seems to make more sense to me.
yeah. Yeah. Because like Bernoulli's is essentially just the same thing, conservation of energy.
Mhm.
It's just per volume. Because if you
Okay.
take this, right, like K plus U, and you just divide it by volume, right? Like 1/2 mass mv squared plus mgh. If you
Mhm.
divide this by volume, right? The m over volume would be density. So
Yeah,
you
okay.
essentially are doing the same thing as anyway. Uh,
Uh,
it's just that there's an additional pressure value here,
yeah,
but still pretty much, yeah, it's still like Bernoulli's is still going to give you a conservation of energy formula, but per volume.
that makes sense. Okay. Yeah, that makes sense. All right. Thanks for going over that one. I'm gonna shut that real quick. Let's see, this was the
Mm-hmm.
water flowing through. Okay, yeah. So I did get that one right.
Mm-hmm.
I was wondering about, this was the Quezel's law, I think, if I
Yeah,
remember right.
yeah, yeah. That
Yeah.
that one's known to be like one of the only, I think, yeah, one of the only formulas that has like something to the fourth power in it. Yeah.
Yeah. Okay. Cool. And right. Oh yeah. Which diagram correctly represents the electric field generated by an isolated negative point charge?
Yeah.
Uh,
So just by convention, electric field lines go from positive to negative.
okay. So okay, got it.
Yeah.
So that's pretty self-explanatory.
Mhm.
two charges, Q1, Q2, separated by distance R. Electrical force between two charges, magnitude of charge were both doubled. Distance between them is quadrupled. What would be the electrical force between them? Let's see. Charges, Q2 separated by distance. Is this squared cubed law? No, that's squared cubed.
You're on the right track.
Yeah, inverse square law, right?
Yep.
Yeah. So what's that? That's so yeah, I think that's why so it's doubled, so it's the inverse squared, so 1/2 squared. So it should have been 1/4, not 1/2.
Yeah, right. Because you could even do it like in parts. Like, so we know that this is right. And so now I'm going to do the first part, which is doubling the charges. So I'll do 2Q1, 2Q2 over R squared. This gives me 4Q over R squared. So if I double each of the charges, the force I get is 4 times as much, right?
Okay.
So that would
Yeah.
be this right here. Now I'm going to make the radius quadrupled. So 4R squared gives me 16R squared, right?
Yeah.
So that alone would give me a force that's 1/16, right? So now I'm going to just kind of multiply the two, like 1/16 times 4 from up here would give us 4/16, which is 1/4. And there you go.
Okay. Does the inverse square law apply to this?
Yep. Because like it's
Yeah.
if you just did the relationship between the radius and the force, that would be an inverse square relationship.
Right.
But if it was between the charges, it would be a proportional one.
Proportional. Okay.
Yep.
Got it.
Yeah, these types of questions are very common. But yeah.
Yeah, the relationships between variables.
Yep.
Okay. Sweet. 0.6 Coulomb flows through an electric circuit. 30 milliseconds. What is the current? So, okay, so no, it's charge per, so charge per second. Yes. So I have 6 times 10 to the negative 1 over, what is that? 3 times 10 to the negative 3. So,
Did you say
sorry, 30. So what I guess it's 3 times 10 to the negative 2 then. 30 milliseconds.
yeah? What I usually do when I see these is I turn it into seconds, like
Seconds.
as I write it, but I'm not gonna turn it into like 3 times 10 to the something like that.
Okay.
Keep it at 30. So, and then because that way I just have to tack on to the end, times 10 to the negative 3.
Okay.
Like, because there's an extra step where if I wanted it to be like a 3 in the front, it would be like left subtract right add. So this would be
Yeah.
2. But I always feel like that I can make a mistake if I do that.
Mhm.
I would just leave it as the 30. And then I'd tack on the E -3 at the end.
Okay. Yeah, that makes sense.
Yeah. And yeah, and the values make uh kind of work out here because 6
Yeah, 6 and 3, 2.
that many times, right? Um,
Yeah,
so 1/5 times 10, and then it would be -1 minus negative,
minus
in other
minus.
words, 3 minus 1 or 2 this, and then 1/5 is 0.2. So move that over twice, you get 20.
Got it. Yeah.
So you have the right
Okay.
idea. I think you just put
Yeah, I did the wrong. Like I think I did exactly what you said. That you were trying to avoid there.
oh yeah, yeah. Yeah,
Okay.
I have to tell myself like if I wanted to go from this to this, I'm like I literally have to say to myself like 30 to 3, I'd say left subtract, right
Mhm.
add. So
Right.
or left add, right subtract. And like I don't trust myself doing that, so I just would get into the habit of just writing it like this. Let's say that we had 300 nanometers,
Mhm.
right? I'm not gonna do 3 times 10 to the -7 or something like that because I don't want to possibly make a mistake. I'm just gonna write 300 e -9 meters.
Yeah.
So
Okay. Yeah, that's a good tactic.
Mhm.
Okay. Let's see. That's a pretty easy one. Wires X and Y are made of the same material and have the same length. Wire X has double the diameter of wire Y. What is the ratio of resistance of wire X to resistance of wire Y? Um, okay. I did not remember the so it was density times the length over the
so that row is actually
oh yeah
something called resistive.
resistivity, right? Yeah.
Um, but yeah, you want to know that relationship because like so let's say this is our wire here. I don't know if I did I ever draw anything like this before for you?
I don't think so. No.
Okay. So these are like copper atoms for like some wire, and then these are electrons
Mhm.
that flow through it. And you know, electrons that flow through it will like brush up against the copper atoms, producing friction, which means like heat will be produced. And let's imagine, so I'm going to draw like a side view of this. And, let's say that, well, let's say these are all like the copper atoms here. Um, and, the electrons are traveling through this way. So the more they brush up, the more they travel through this, the more they brush up against the copper atoms, and the more they brush up against the copper atoms, the more friction and resistance is being met.
Okay.
So
Yeah.
it would make sense that if the longer we make this, the more resistance there should be, right?
Yeah. More resistance, and then like the wider it is, or the greater the circumference of the wire, the less resistance you have. If you
Yeah,
have you have a really small, thin wire, small, thin, and long wire, it's just going to be, yeah, it's not going to, the electrons won't flow as easily as they would through I
yeah.
guess, a thick wire. Yeah.
So if we increase the area like this, it gives the electrons a lot more paths to travel through. Uh, and thus this can minimize the resistance. So that's why resistance is proportional to the length. It goes up as length goes up, but it goes down as the area goes up.
Okay.
Now,
Oh, I see. Okay, that makes more sense now, because now it's comparing resistance to the resistance of the wire to the resistance of the other one. Okay,
yeah.
double the diameter.
So let's say we have these two resistors in series. If you add them, you're essentially creating one long resistor, right? And if
Yeah,
it's long, the longer it is, the more resistance there is. So that's why for resistors in series, to find the equivalent resistance, you must add them. Because if you
yeah,
add them, you get a higher value for the resistance, right?
right. And then parallel, it's 1 over
Yeah.
the sum of the resistance.
Yeah. If you're adding resistors in parallel, you're essentially doing like increasing that area to give the electrons more paths to go through. So the resistance will decrease. And when you have a reciprocal sum, it means you're gonna get a smaller value rather than larger like you would in the series. So that's why there's the reciprocal sum for adding resistors in parallel. Uh, the opposite would be true for capacitance because that would be proportional to area and inversely proportional to length or distance. So
Right. So you add capacitors in series, it's
yeah,
1 over the sum of the capacitance.
yeah,
Parallel, it's just the sum of the capacitance, right?
exactly. Yeah.
Okay.
Yeah. That's why,
Gotcha.
yeah, it helps to know like, why the formulas are the way that they are. So,
Yeah,
yep.
absolutely. Okay. Cool. But let's see. So it's saying dx and dy, t times dy. Cross-sectional area of wire x is 4 times bigger than the cross-sectional area of wire y. Where did that come in? So you have dx is equal to 2 dy. Sectional.
So I was gonna ask something like this actually, like when we just did that previous question, but I was
Yeah.
gonna ask, um, if you like that, I think it was like a question about quadrupling the radius or something, um,
Yeah.
but so what's the relationship between? So they're telling us that they're doubling the diameter, and but we want to think about the area, right?
Yeah. 2
Area,
pi. That's what it is. Okay. That
yeah,
makes sense. Okay, that's where 4 comes in.
yeah. What were you? What did you say for that? Then?
Is 2 pi r,
Uh,
right? Is that right? Or
I think you're thinking of circumference,
yeah, maybe not.
but in order for something to be an area, it must have uh units that are squared, right?
Okay.
So like kind of like pi r squared,
Oh, okay. Yeah,
right?
that's right.
So area would be proportional to the square of the radius, right?
Where the radius? Yeah.
And diameter is essentially just another way of kind of saying that. So if you double the diameter, you would get 4 times the area.
Okay. Yeah.
So
Okay.
that's
That makes.
Mhm.
All right. Yeah, I was thinking. Yeah, forgot how to calculate the area of a circle.
Yeah, yeah.
I, yeah.
Doesn't even really have to be like necessarily that. Just
Mhm.
because so like if something's in one dimension, it's like a length, but in two dimensions, it would be like, let's say, length times width. And well, length would be, let's say, in meters, but length times width would be in square meters. So area has to have has to be in 2 dimensions. That's why like square footage or something is like something that you use to measure like how much space you have in like a house. So in
Okay. Yeah.
like even if it wasn't a circle, right? If it was like whatever, a square, let's say with a side S, right? The area would be S times S or S squared, right?
Right.
And for volume, it would be something with a cubed.
Yeah. Calculating it in 3 dimensions. You
Yeah.
have a length times width times a a z direction
Yep.
for height.
Yeah.
Yeah.
So let's so hypothetically, if we double the diameter, what would happen to the volume?
Hypothetically, if you double the diameter, um, so you have length times width. Or sorry, you have pi r squared
Oh
times
yeah.
height, and you're also
Yeah.
so you're proportionally increasing your area. So you're also let's see, double your diameter. Everything's proportional, so you'd also double the volume,
So
right?
so let's think about the relationship between volume and dimension.
Um,
Like it would be in 3 dimensions, right? Volume.
right. Mhm.
So if we could say that area is proportional to like a square term, but volume would have to be proportional to a cube term, right?
Oh, I see.
So if you double the diameter, the volume should increase by,
Factor of cubed. So yeah, it would be going up by 8.
yep,
Factor of 8. Yeah.
times as much, right?
Yeah.
Yeah.
Okay.
So
Yeah, I guess.
you don't have to necessarily know this formula, but in order for something to be an area, it must have 2 dimensions. So you want to make sure that you have something like square meters or something. And then if it's volume, it'll be cube something.
Okay. Yeah, I think the way I was just thinking about that was just the wrong way. I was thinking about the I guess the formula of calculating a volume of I don't know cylinder. Like I was okay if I were to double my diameter of some like cylindrical thing, and I would be or if I were to double my diameter, it would still be pi r squared times the height. And it's like, does that change? Is it just still proportionally changing it by squared or?
Pi r squared times height. So
Yeah,
the r is in meters, and if it's squared, it's in square meters. The height
yeah,
meters, right?
also meters.
So this would
Yeah,
be cubic meter.
just cubic meters, right?
So
Okay,
just by virtue of being volume.
yeah,
So
that
so you
makes sense.
think about like a length or a width on its own or a height on its own is going to be 1 dimension. So like a meter. And area would have to be in 2 dimensions, so square meters, and then volume 3 dimensions. Yeah.
Okay,
Mhm.
awesome. Well, I'll probably have to end it there
Yep.
today if that's all right.
Yeah, yeah.
Yeah, thank you. That's thank you for going over this with me.
Yeah,
That was really
totally. So let's see. What are you doing moving forward? I think you said you're gonna start taking like a test or something.
yeah. I was gonna do so. I know that on that schedule, we were going to start doing our like the blueprint exam. So I was going to do full length one for blueprint.
Yeah. Got it.
How would you? So do you think that's the best next step going forward? To start, because my test is on the 26th of July.
Yeah. So did you finish? Oh yeah. Wait. Okay. I was gonna say to because so far you're still going over this content diagnostic, right?
Yeah, so I'm still going through the so I'm getting through the biochem stuff now, and also going through the psych stuff. So yeah, I'm still getting through all that stuff.
Yeah.